Okay, let's look at the last type of hypothesis test, which is for variance and standard deviation. So in the past, when we were looking at mean and proportion, you had the choice if you wanted to use the p-value method or the critical value method. We don't have a choice this time. When it comes to variance and standard deviation, we're only going to use the critical value method. So the recipe is the same for the other types of hypothesis test. We're going to determine what the critical values are. Now we'll use the chi-square distribution. We'll be given the alpha value and the degrees of freedom. Then we can go to the tables to determine what the critical values for chi-squared are. Now, as usual, there are three types of problems: left-tailed, right-tailed, and two-tailed. So the alpha value is the area in the tail in the blue part. However, if we have a two-tailed test, we have to split that in half. So we take the alpha value and divide by 2. Let's look at this example here. Now there is an error in the text here. It says left-tailed, but really we need to do a right-tailed test first. So n is 26, alpha is 0.1, right-tailed test. As usual, draw your picture. This is a right-tailed test, so we'll be over here somewhere. We're looking for the chi-square critical value that separates reject from fail to reject. Now, the alpha value is the area in the tail, which is 0.1. The chi-square distribution always uses the area to the right, so the area to the right is 0.1. N is 26, therefore degrees of freedom are 25. Now we have everything we need to go to the table. Go to your chi-squared table. The area to the right is 0.1, so we go to the 0.1 column. Degrees of freedom are 25, so we go down to 25. The chi-square critical value is 34.382. Okay. Now, if we do a left-tailed test, similar procedure, but we'll have to do some more thinking. Find the chi-square critical value for a left-tailed test when n equals 11, alpha equals 0.01. Okay, draw a picture. This is a left-tailed test. Alpha is 0.01. All right, we need to find the chi-square critical value. Now we have to be careful here. The area in the tail is 0.01. We need the area to the right. So we do 1 minus 0.01 gives us 0.99. Degrees of freedom are 10. So if we go to the table, the area to the right is 0.99. Go to the 0.99 column. Degrees of freedom are 10. 2.558. Okay. All right. Now, naturally, if we've done left and right, let's look at a two-tailed test. So this time we're going to have 2 chi-squared left and chi-squared right. N equals 9. Alpha is 0.05. So on our sketch, one on the left and one on the right. Now let's be careful here. The alpha value, 0.05, is the area in both tails. So if I want to know the area in one tail, we have to divide that by 2. 0.025. Now, if there's 0.05 in the tail, how much is in the middle? Well, it's 1 minus 0.05, which is 0.95. And now that we have these areas, we need those for the table. So reject on the left, fail to reject in the center, and reject on the right. Let's start with chi-squared right. The area to the right of chi-squared right is 0.025. N is 9, therefore degrees of freedom are 8. So if we go to the table, we go to the 0.025 column, go down to degrees of freedom of 8, 17.535. Now on the left, let's be careful. I need to know the total area to the right, which is the center plus the area on the right, so I have to add those two things together. That'll give me 0.975. And this is the number we'll use when we go to the table. Go to the 0.975 column. Go down to degrees of freedom of 8, 2.180. And now we have the critical values. Okay. Now, as usual, when we're using the critical value method, we're going to compute the test statistic. We'll use this formula and we'll compare it to the critical values to determine if we reject or fail to reject the null hypothesis. So as usual, state the claim and identify the null and alternative hypotheses. The level of significance will be given to you in the problem. Identify degrees of freedom. With that, you can go to the table and determine the critical values. That tells us where the rejection regions are. Compute the test statistics. Compare that to decide if you reject or fail to reject. And finally, interpret it in terms of the original claim. So let's try this out. So we have this dairy processing company claims that the variance of the amount of fat in the milk is no more than 0.25. You suspect this is wrong, and in a random sample of 41 milk containers, there's a variance of 0.27. At the 0.05 claim level, is there enough evidence to reject the company's claim? So this dairy producer needs to know the amount of fat in the milk so that they can label it skim, whole, 1%, 2%, what have you. But it's not going to be perfect every single time. There is going to be some variance in there. Now you want to minimize this variance for quality control. So he's claiming that it's no more than 0.25, which is the limit. It means that it's going to be less than 0.25. Okay, so start with the claim. We're talking about the dairy producer's claim. that the variance is no more than, meaning less than 0.25. Now, if it's no more than, it means it cannot go over, but it can be equal to. All right, state the hypotheses. The claim contains equality, so it goes in the null. The alternative will be the complement greater than 0.25. Okay, what else did they give us in this problem? Sample variance, S squared, is 0.27. Alpha is 0.05. N is 41. Sketch the figure. Because the alternative is greater than, this means this is a right-tailed test. So we're over here somewhere. Okay, now the alpha value is 0.05. That's the area in the tail. That is the area to the right. N is 41, which means degrees of freedom are 40. Go to the table. 0.05, degrees of freedom are 40. 55.758. Now, that is the border that separates the reject from fail to reject. We need the test statistic. N minus 1 S squared over sigma squared. No, let's be very careful here. Sample standard deviation, sample variance was given to us. The population standard variance is assumed from the claim. So we're going to use 0.25. So this is 41 minus 1 times S squared, which is 0.27. Now be very careful here. We are not going to square this because S squared represents variance. We have the variance, so there's no need to square it. Now, if this were a standard deviation problem, we would square it, but it's not. Population variance, we assume, is 0.25. So we get 43.2, which is less than 55.758. Therefore, fail to reject the null hypothesis. Conclusion. Go to the same hypothesis testing diagram. Does the original claim contain the condition of equality? Yes, it does. Move to the right. Do you reject the null hypothesis? No, we did not. Fail to reject. There is not sufficient evidence to warrant rejection of the claim. we should say the dairy company's claim that the variance, make sure to get the parameter in there, of dairy fat is no more than, what was it, 0.25. And we're done with the problem. Okay, let's go back to the text. Now, this is a typo here in the text. They use S squared. That is incorrect. We need sigma squared to represent population standard deviation. So we have the alpha value and we have degrees of freedom. We have the critical value, which was our 55.758. Compute the test statistic. Now, where I disagree with the text is you should have drawn the picture already before this. So the test statistic lands in the beige area. We fail to reject the null hypothesis. There's not enough evidence at this level to reject the company's claim. Okay, let's try a different problem. So let's use standard deviation this time, which is going to be very similar. So what's going on this time? We have a company claims the standard deviation of the length of time it takes for incoming calls to be transferred is less than 1.4 minutes. A random sample of 25 incoming calls has a standard deviation of 1.1 minutes. But the 0.1 level is enough evidence to support the company's claim. So what the company is doing is they're looking at how long it takes to transfer a call. Now, the answer here is we're looking for consistency. So the standard deviation is, they're claiming, is less than 1.4 minutes, which means most of their calls are routine. They're kind of taking out the same amount of time. Okay, let's state the claim. Claim. Now be careful this time. We're not talking about variance, we're talking about standard deviation. The company claims that the standard deviation of time is less than 1.4 minutes. State the hypotheses. The claim does not contain equality, so it goes in the alternative. Therefore, the no is the complement greater than or equal to 1.4. Draw your picture. That's wrong. Because the alternative is less than, this needs to be a left-tailed test. That's more like it. And that'll separate reject from fail to reject. Okay. What do they give us in the problem? The sample size is 25. The sample standard deviation S is 1.1. Alpha equals 0.1. Now the area in the tail is 0.1. We need the area to the right. 1 minus 0.1 is 0.9. N is 25, therefore degrees of freedom are 24. Okay, let's go to the table. The area to the right is 0.9. We go to the 0.9 column, go down to degrees of freedom of 24, 15.659. So that's the cutoff between reject and fail to reject. Find the test statistic. Now, what makes this problem different from the other one is that we are given standard deviation, not variance. So we do have to square this. It's 25 minus 1 times sample standard deviation is 1.1 squared. The population standard deviation is assumed from the claim to be 1.4. (14.82), which is going to be to the left, but not by much. Therefore, our decision is to reject the null hypothesis. So it lands in the rejection region just a little bit to the left. Okay, conclusion. Does the original claim contain equality? No, it does not. Go down. Do you reject H0? Yes, we do. The sample data support the claim that we should say the company's claim that the standard deviation of call times is less than 1.4 minutes. And we're done with the problem. Okay. State the claim and hypotheses. So they did it correctly this time. They used sigma here. We need to draw the picture first, then go to the table and get the critical value, compute the test statistic. Because it falls to the left of the critical value, we reject the null hypothesis. There is enough evidence at the 10% level of significance to support the claim that the standard deviation of time is less than 1.4 minutes. Okay, so what's next? Sporting goods manufacturer claims that the variance of the strength of a certain fishing line is 15.9. A random sample of 15 fishing line spools has a variance of 21.8. At the 0.05 level, is there enough evidence to reject the manufacturer's claim? Okay, so we have this sporting goods company. They make fishing line. The line has to be so strong so that you don't lose the fish. But if you make it too strong, it becomes expensive to produce. So we're looking at the variation. So we're looking at quality control, making sure that most of them are made the same. Okay, let's state the claim. So the sporting goods manufacturer claims the variance is equal to 15.9. state the hypotheses. The claim contains equality, so it goes in the null hypothesis. The alternative will be not equal to. So when we draw a figure, we'll have a two-tailed test because the alternative was not equal to. Which means we're going to have two chi-squared critical values. In the sample size is 15, alpha equals 0.05. The sample variance is 21.8. Okay, now let's be careful here. The alpha value is 0.05, but that is in both tails. We have to split that two ways, so we have to divide this by 2. So this is 0.025 over here, 0.025 on the left. If there's 0.05 in the tails, that means there's 0.95 in the center. Okay, let's go to the table. Area to the right is 0.025. We go to the 0.025 column. N is 15, which means degrees of freedom are 14. 0.025, go down to 14, 26.119. Let's label this is right. There we go. For the left, we need the total area to the right, which is the 0.95 plus the 0.025, which is 0.975. Go to the 0.975 column, go down to 14, 5.629. Now, we know the cutoffs for reject and fail to reject. Let's get the test statistic. Now, be careful. We are doing variance. We have sample and we'll assume population variance. When we plug this into the formula, there's no need to square it. 15 minus 1. Sample variance is 21.8. We assume the population variance from the claim is 15.9. Do not square that. $19.2, which is going to land in the center. It's between 5.6 and 26.1. Therefore, we fail to reject the null hypothesis. Conclusion. Go to the diagram. Does the original claim contain equality? Yes, it did. To the right. Do you reject H0? No, we fail to reject. There is not sufficient evidence to warrant rejection of the claim. Let's see, we should say the manufacturer's claim. that the variance for fishing line strength is 15.9. And we're done with the problem. Okay, state the claim and the hypotheses. Determine the critical values. Sketch the rejection region. Compute the test statistic. This time, it landed in the center, so we fail to reject. There's not enough evidence at this level to reject the claim that the variance is 15.9. And we're done.